Today, we're diving into the world of enzyme kinetics. Sounds technical, I know, but stay with me. By the end of this talk, you'll see how the dynamics of enzymes and their behaviors help keep us alive every single day. And who knows, you might even find enzyme kinetics fun. Imagine enzymes as tiny machines or even theme park rides. They're hardworking proteins that catalyze reactions, breaking down or building up the molecules we need to survive. The study of enzyme kinetics looks at how fast these reactions happen and what factors can speed them up or slow them down. Let's start with the basics. Every enzyme has a favorite molecule, called a substrate, which fits like a lock and key. When an enzyme binds with a substrate, it speeds up the reaction, kind of like adding an extra lane to a busy highway. But enzymes can't work endlessly fast. They have limits, which brings us to two key concepts: the Michaelis-Menten constant, Km, and Vmax. Let's talk about the Michaelis-Menten constant, or Km. Km tells us about the enzyme's affinity for its substrate. In simpler terms, Km reflects how much our enzyme likes its substrate. If an enzyme has a low Km, it has high affinity and doesn't need a ton of substrate around to work at half its max speed. Think of it like a close friend who doesn't need a lot of convincing to hang out. On the other hand, a high Km means that the enzyme has low affinity and is a bit pickier. It's like that friend who takes a lot of coaxing to come out for a night on the town. So in essence, the lower the Km, the stronger the attraction. The higher the Km, the weaker it is. Next, we have Vmax. Think of this as the fastest speed our enzyme can work when there's an unlimited supply of substrate around. Vmax represents the enzyme's maximum capacity, or its top speed, if you will. When all enzyme sites are busy with substrates, the reaction hits Vmax. It's like a roller coaster operating at full capacity. No more seats are available, and no matter how many more people are in line, it can't go any faster. Here's the cool part: Vmax depends on the amount of enzyme present. Increase the enzyme concentration, and the Vmax goes up because there are more seats for substrates. Reduce the enzyme concentration, and Vmax comes down. So, in essence, Vmax is directly proportional to the enzyme concentration. More enzymes, higher top speed. If we were to plot enzyme activity on a graph, we'd usually see a hyperbolic curve, which shows us the enzyme's reaction rate as it picks up speed with more substrate. This curve represents what we call Michaelis-Menten kinetics. At low substrate levels, the enzyme is like a car pulling out of a driveway. It's picking up speed. But as more substrate is added, the enzyme reaches Vmax, maxing out its speed like a car hitting top gear on the highway. This hyperbolic curve is what we see in most enzymes, those that don't talk to each other and work independently. But some enzymes like to work in teams, which brings us to cooperative kinetics. Now, not all enzymes operate solo. Some, like hemoglobin, work together in what's called cooperative binding. Let's say we have a cooperative enzyme. When one substrate molecule binds, it encourages others to join in, kind of like when one person starts clapping and the whole crowd joins in. This behavior creates a different shape on the graph, a sigmoid curve, which is an S shape. Take hemoglobin as an example. When one oxygen molecule binds, it changes the structure just slightly, making it easier for the next oxygen to bind. This cooperative behavior is essential for hemoglobin's role in carrying oxygen through the bloodstream efficiently. So, in summary, a hyperbolic curve usually means the enzyme is working independently, while a sigmoid curve suggests teamwork through cooperative binding. Part 6: Why Enzyme Kinetics Matter. You might wonder, why does this all matter? Well, understanding enzyme kinetics is crucial in medicine, pharmacology, and many other fields. For example, many drugs work by inhibiting enzymes. Knowing an enzyme's Km and Vmax helps scientists create more effective medications by fine-tuning how drugs interact with target enzymes. Take antibiotics, for instance. They inhibit bacterial enzymes essential for survival, effectively shutting down the theme park rides for those harmful bacteria. Also, enzyme kinetics helps us understand conditions like enzyme deficiencies and metabolic disorders, leading to better treatments and management. In conclusion, enzyme kinetics may sound complex, but it's all about understanding how enzymes get the job done. Chem shows us how strongly an enzyme is drawn to its substrate. Vmax tells us how fast it can work, and those curves, hyperbolic or sigmoid, show us if they're working alone or as a team. So next time you hear about enzyme activity or see a medicine ad, remember, there's a world of enzyme kinetics at play behind the scenes, keeping everything in balance. Thank you for joining me on this journey through the microscopic theme park of enzyme kinetics.